Let's see. I'm going to talk about some work that we're doing at the University of Tennessee, and we're doing this with a number of collaborators who are on my team. Their names are listed here. I'm not going to have time really to go through and give credit to all the people that I should. Okay, so what are we doing? Magma is a project to take some of the software that has been developed, I'll say in the last century, and move it forward to the architectures that we have today. And we're looking at dense matrix problems. So we're looking at dense linear systems of equations as well as eigenvalue problems, and taking that software and putting it on machines that have hybrid architectures. So we're looking at putting it on systems that have multiple GPUs. We're looking at trying to organize the computation so it can be effectively or efficiently done on a large number of processors. And we also have the notion of going to, of course, distributed memory systems. And we're starting to do some work with sparse matrices as well on these accelerators. Okay, so just to begin, this is the top 5. This is the top 10 list, if you will. So these are the 10 fastest machines. The way to read this is the machine number 1. It's at a center in Guangzhou, China. It's based on Intel processors plus Intel coprocessors. It has 3 million cores. I still have a hard time with that. 3 million cores on this machine. And if you're going to use it at full scale, use the whole machine, and get very efficient things, you need 4 threads of execution on that. So you'd have to manage 12 million threads of execution. It achieved 34 petaflops. It ran at 62% of the theoretical peak performance for the architecture, and it used about 17, 18 megawatts of power. Right, so power is a big deal today. 1 megawatt year in the US is $1 million. So that machine, just to turn it on, is about $18 million a year for power to go into that machine. So power is, really a crisis for our systems today. And this is a measure of the efficiency. So it's about 2 gigaflops per watt is the way to read that. And we can scan down the list. There's a few notable things. The first thing is lots of cores in the top 10 machines. These machines are intended for doing large-scale scientific problems, right? And it's anticipated that one application will run on that machine. They want to solve the most challenging problems. You're not going to run thousands of applications. You're going to run one application to devote the whole machine to doing that one application. And so power is a big deal on these systems. The smallest one is 1.5 megawatts of power. And the other thing we noticed that they're using accelerators. Accelerators from Nvidia are being used on these machines, and also from Intel are being used. So 5 of the top 10 machines use accelerators today. If we take a look at the accelerator picture and how it's evolved over time, this is looking at just that scenario. So here, starting in 2006, going to today, this is a picture of how many machines use hybrid architectures. So we see that Nvidia has the largest share of those machines. Roughly 50 of the machines on the list use Nvidia. So 10% of the list is basically using Nvidia processors. And then there's about 12 machines, maybe 11 machines or so using Intel Xeon, not 11, probably closer to 20 machines using Intel Xeon Phi processors to accelerate the performance. And a couple of machines are using AMD's ATI accelerator in that way. And that's a trend that we're going to see continuing into the future. I'm sure that we'll see more and more of these machines. So more than 10% using Nvidia products. Please. Why is there a dip? Yeah, why is there a dip? I have no idea. So, right. So there were a number of machines that were small machines that were using accelerators early on, and as the list progresses every year, the top and bottom list goes up. The requirements to get on the list goes up, and machines are whacked off, and new machines go on the list. And what we have seen is the replacement rate has been going down for the top 500 list. That's sort of an interesting facet. If you came to the BOF yesterday, there was some discussion about that. And that's caused this dip, and then it has accelerated. That has increased. The number of accelerators has been increasing in recent time, right? And bigger machines. So yeah, that's an interesting fact. Why is that down in that time period? Okay, so what are we doing? We would like to develop software. Hope that doesn't fall. We'd like to develop software for dense linear algebra. This is a historic graph showing you where we've been. So when I started my career, I started with the development of that package, LinPack. LinPack is a package of linear algebra software for solving dense matrix problems. And it was based on vector operations. It was based on doing vector operations. The first vector machines were just coming out at that time, and we wanted this package to be very efficient on those machines. So that was designed around the level 1 BLAs. We only had one level at that time. In the 80s, it was recognized that that design for software was not going to be very efficient. Designing for vector operations on a cache-based machine gave terrible performance. So you had to do more blocked operations. You had to be able to use matrix quantities, matrix operations. And that's what LAPACK is about. It blocks things and it tries to effectively use cache. And LAPACK was a replacement then for the LinPack library. That was a 10-year window. And in the next 10 years, distributed memory machines came out. We had message passing. MPI was created. And we took that LAPACK software and redesigned it to work on those distributed memory machines. And that was the next generation. Another 10 years went by with that software. Today, that software does not run very efficiently on a multi-core hybrid system. It can work, it works fine, it gets you very good answers, it's very state-of-the-art algorithms in there, but the software doesn't run very efficiently. So we're redesigning that software. We're redesigning it to look at multi-core and, of course, distributed systems. That's Plasma. If you have a heterogeneous set of processors, Plasma's your guy. If you have a heterogeneous set of processors, then Magma's the thing to replace it. Magma's the replacement, if you will, for some of that software in that time period. Do you have a question? Plasma's so it's all the same processors, that's right. So it's a homogeneous. If I said heterogeneous, I misspoke then. Set of processors. So that's the way to think of it. Those packages run very efficiently. They use a different programming style. The programming style that's used now in these packages is not a loop-level parallelism. It's not a fork-join parallelism. If you were at Charles Lyserson's talk this morning, he talked about a Dataflow model. These algorithms use Dataflow. They use a Dataflow model to effectively try to use all the processors. There's a directed acyclic graph that's built, and that DAG is then executed on the underlying hardware. That's what's going on in Plasma, and that's what we're putting into the next version of Magma. Okay, so what is Magma? So matrix operations on GPUs is the way to think of it. It's a replacement, if you will, for those packages. It's available today. You can go and download the software and build it on your machine. The version that we have today is built on top of CUDA, of course, and it effectively uses the GPUs that are available to your system. So here's a list of collaborators. We couldn't do this ourselves. I certainly didn't write the software myself, but my team at the University of Tennessee, my colleague at Berkeley, Jim Demmel, a former postdoc who now works at the University of Colorado, Denver, colleagues who work in France. There's one in the back row here, Mark, who's helping us, and some colleagues out in KAUST in Saudi Arabia. We have some former postdocs who are now working at KAUST and helping with the effort. So it's a community project, similar to the way LAPACK and ScalaPack were built. Those were community projects, getting the community involved, helping to really build a solid package based on what I'll call state-of-the-art algorithms. So here's some of the features. It's designed for high performance. It uses multiple precision, so there's a single, double, complex, and double complex version of all the software that we have in our library. And it also uses a mixture of precisions at a certain, during certain things to boost performance. You know that single precision on commodity processors, single precision is twice as fast as double precision. And if you do operations on single precision operands, you have less data movement. Data movement's critical for all computations. It's the killer in terms of performance. So minimizing data movement and getting twice as fast is a good thing. So we designed some of the algorithms to use a mixed precision. They do some of the operations in single, and then they do critical things in double, and try to get the same precision that you would have gotten had you done the whole thing in double precision. So we can run faster. You know, on some of the Nvidia products, there's a factor of 3 between single and double precision. So getting that factor of 3 is really a good thing. We have algorithms which are out of, they allow you to execute matrices which are much larger than the GPU memory. GPU memory is small. What are we at? 6 gigabytes on the GPU. So we can now do much bigger problems by using the host memory, shuttling data from the host memory back and forth. Think of it almost like in the old days we used the word out of core. Core had a different connotation in that case. And it supports multiple GPUs. So that's sort of the focus or the direction that we're going with in Magma. So here's a cartoon, if you will, of what's supported. So we support CUDA clearly, so Nvidia products are supported. We support OpenCL, so there's an interface that allows all the software to be used with OpenCL, and there's an interface which allows most of the software, all the software also to be used with Xeon Phi processors. So here's our checklist. If things aren't checked, it's just because we haven't gotten around to doing it, right? So things at some point will be checked off. So there are linear solvers, there's eigenvalue problems, there's multiple precision things going on, there's multiple GPUs are supported. We have an extensive set of test software that was developed under the LinPack project. We have about 500,000 lines of code, which really stresses the software. It gives us confidence that the algorithms we've implemented are correct numerically, and that they don't have, it was built correctly as well. So we can at least have some assurance that it's there. And that software is being used here to verify this package. We have a Windows version if you wanted it, and then there's a Mac OS version as well to go along with that. And here's a cartoon of performance. This is running on a system which has 16 cores. So the host is a 16-core. It's a board which has 2 sockets, 8 cores per socket. And this particular implementation uses 2 GPUs, or there are 2 GPUs on that board. So that's the host board, if you will. And if we ran the code, if we ran MKL, so that's the Intel's math kernel library, on that, on just the multi-core part of the machine, we get performance that looks like this for an LU factorization. We want to solve a dense matrix problem. We want to solve a system of equations where the matrix is general. If we use one of the GPUs, our code gives you performance which is a little bit better than we got before, and 2 GPUs doubles that improvement. So we're getting quite a bit of improvement overall, and the code is running about 2.3 teraflops is the performance that we're seeing out of that particular code with those 2 GPUs. Okay, so that gives you a hint. And then, you can do this. This is running on the previous generation of Nvidia processors. We could do this with single, double, complex, and double complex. So now the data types are changing. So I got a single precision 32-bit representation of the matrix. I solve it, and I get this performance. I get this performance here. That's a single precision. Double precision performance is the lower line, so about half of the performance. That's because it takes twice as long to do the floating point operations, and you're moving more data around, so you're being tested there. Complex arithmetic, you're doing more floating point operations per data item with complex arithmetic, so that boosts a little bit the performance, and we see that with the blue line. And this is double precision complex floating point arithmetic, and again, there's a big boost in terms of performance there. I'm sorry. This is the 32-bit, and this is the 64-bit complex arithmetic. So you see that boost in terms of performance, and then the performance for the 64-bit floating point arithmetic. Okay. So again, we want to use all of the processing capability we have on our board, and Magma is structured like this. We call that a hybrid approach. So if it has multi-core, we want to use the multi-core as well as using the GPUs. So we're going to be using both parts of that system. We're not going to waste the system, parts of the system, just to exploit the GPU. So the code that we have is structured or put into a modular form where we can almost take the existing LAPACK code and modify it, I want to say with simple text edits, to get it into a form which uses a version of the BLAs that exercise things on the GPU. So they're responsible for moving data over correctly to the GPU. They're responsible for starting the processing and then getting the results back. So that's these higher level BLAs routines. You see Magma underscore and then some name of a routine for get and put the matrix and look at synchronizing events and look at doing the operations. So that's what I'll call a simple modification of the LAPACK code to get it into shape so it can run and exploit those GPUs. This is looking at what I was talking about earlier, using single and double precision to get a solution to the problem. So the thing to look at here first is the blue line. The blue line is solving it using 32-bit arithmetic. It's using 32-bit arithmetic, and this particular example has one GPU in it. Using 32-bit arithmetic, what we see is the performance looking something like this. If we were to take the code and do 64-bit arithmetic, that's the red line here. So 64-bit arithmetic is the red line, getting more precision, of course, in the solution. But taking longer to arrive at that solution. There's a technique that can be used, and that technique is called iterative refinement. The iterative refinement says you're going to factor the matrix in 32-bit arithmetic and then do a procedure which tries to refine the solution using extended precision at critical parts. If you use extended precision at critical parts, you can actually prove that if it converges, it's going to converge to the 64-bit solution. It's as if you had used 64-bit from the start. So you factor a matrix, that's where all the expense is, and then you do this iterative stuff to go and refine the solution. And if you use that technique, you end up with this brownish line here. So the performance is much better than double precision. I got the same accuracy as double precision. It's a little bit lower than single precision because I do have to do some additional work to get us there. But we end up with exactly the same solution, the same accuracy that we had with that red line there. So it's a much better story. So we're advocating, we have software in our library which effectively does that. Okay, so there's multiple GPU support that can effectively use multiple GPUs, and we end up with performance that looks something like this. The green lines here are for going from 1, 2, and 3 GPUs. These are older versions of the GPU. This is a Kepler implementation just on one GPU. So you can see the improvements that have been made with Nvidia with the newer versions of the hardware. There's software in the package for dealing with eigenvalue problems. I'm not going to have time to go into the details, but there's some very good performance. This is the performance of the old version of the software. We have a new implementation which enhances the performance on 1, 2, and 3 GPUs over what we got on 1, 2, and 3 GPUs with the old version of the algorithm. The new version of the algorithm is a multi-staged algorithm. It takes the matrix and reduces it to a condensed form, and that condensed form is then operated on separately, and then ultimately we end up with the tridiagonal matrix and we find the eigenvalues of that tridiagonal matrix. So some of the current work we're doing is this Dataflow stuff. It allows things to execute in a more modular fashion. It generates basically a directed acyclic graph, and that directed acyclic graph is executed by our runtime system to effectively use various components of the machine. And I'm not going to have time to tell you about this story because I'm running out of time. I'm okay, she says. Okay, very good. So think of it like this. the code that we have generates a DAG, and that DAG is a directed acyclic graph has nodes in it, and those are the operations that we're going to do. Those are the tasks. And think of those tasks as being operations on a block of the matrix. Think of those tasks like matrix multiply, or taking a matrix vector operation on a part of the matrix. And the arcs here are dependencies from one node to another node. Think of those as inputs and outputs that get generated. The runtime system executes that DAG and tries to exploit as much parallelism as possible, right? And when you do that, you end up, this is on a 48-core system. If we look at this graph and look at the coloration that's here, the 48-core system is effectively using this kind of work. This is putting 3 routines together. It factors a matrix, it computes the inverse of a factor, and then it multiplies that inverse times itself. And that's what the computation looks like for those three phases. Working with DAGs, you can actually put together the work so that we don't have to do 3 separate DAGs. We can merge those DAGs. The merged DAG looks like this. It allows for much more parallelism, and we end up with a much more efficient operation. So that's the motivation for expressing things as a data flow model and having a runtime system that can manage a whole group of tasks, not just from one routine, but from many routines. And when we do that, we end up with a pretty nice story in terms of the performance that we see from our software on that set of machines, going up to six GPUs in our configuration. So with that, I think I'm going to have to stop. This work is again, joint work. The software is available. You can go and download the software. We get some funding from the National Science Foundation, from the Department of Defense, from the Department of Energy, as well as Nvidia, and also our partners over at the MathWorks. So thank you very much for your attention. I'd be happy to answer any questions that you might have.